Welcome back. In topic 1, we have learned 1. How to specify heat flux through the Fourier's law. 2. How to specify the thermal boundary conditions and initial conditions. 3. How to apply Taylor series expansion. Now, you're ready for topic 2, derivation of the governing equations. Part 1, general conduction heat equation. A. Derive differential conduction equation in Cartesian coordinates. First, there's a finite system. Due to temperature difference in x direction, y direction, and z direction, there's conduction heat flow in each direction. We're interested in the conduction heat flow value. Second, in order to derive the differential conduction equation, we need to define a differential system. 1. A rectangular differential control volume, which is extremely small, is taken from the finite system with a fixed small size of dx, dy, and dz. 2. The differential control volume has properties of density, specific heat, and thermal conductivity, where density and specific heat are independent of time. 3. The differential control volume has an uniform internal heat generation at a rate of Q triple prime. 4. The 6 boundary surfaces of the differential control volume are subject to conduction in x direction, y direction, and z direction. Third, from the differential system we just defined, we can immediately derive the following. 1. The volume dV of the rectangular differential control volume is the product of dx, dy, and dz, which is represented in equation 1. 2. The mass, dm, of the differential control volume is the product of density and volume, which is represented in equation 2. 3. The heat energy stored in the differential control volume, E sub st, is product of enthalpy and mass. Its time rate, E sub st dot, is the time derivative of stored heat energy, which is represented in equation 3. Since the property specific heat Cp and density ρ are independent of time, both can be taken out of a time derivative. 4. The internal heat generation rate, E sub G dot, is the product of internal heat generation rate, Q triple prime, and volume, which is represented in equation 4. 5. On the differential control volume boundaries, all the energy into the system minus all the energy out of the system across the boundary is the summation of all conduction heat flow into the system and out of the system in x direction, y direction, and z direction. 4th, what is the goal? At this point, you may wonder what we're doing here. 1. For this finite system, we have discovered that due to the temperature difference, there's a conduction heat flow in x, y, z direction. And we're interested in the conduction heat flow values. 2. In order to get the conduction heat rate values, we need first to obtain the temperature profile from solving the differential conduction equations, and then to use the Fourier's law to derive the heat rate equation. That's the reason we derive the differential conduction equation. 5th, how to do it? 1. We apply the first law, energy balance, to the differential control volume to yield equation 6, where energy into the system minus energy out of the system plus energy generated within the system is equal to the energy stored in the system. 2. Plug in equation 3, which is energy stored in the system, equation 4, which is energy generated within the system, and equation 5, which is all the conduction heat flow into the system and out of the system in x, y, and z direction to yield equation 7. 3. Apply Taylor series expansion and the Fourier's law to equation 5 for each term. In x direction, A, the conduction heat rate difference in location x and location x plus dx is represented by its derivative using Taylor series expansion. B, the heat rate Q sub x is the product of heat flux and surface area, where the heat flux is represented by the Fourier's law. The surface area dAx is perpendicular to the Qx, which is dy times dz. C. Replace Qx with 8.1 d. Since dy dz are fixed, both can be taken out of a derivative partial x to form the differential control volume dV. In y direction, A, the conduction heat rate difference at a location y and a location y plus dy is represented by its derivative using Taylor series expansion. B, the heat rate Q sub y is product of heat flux and surface area, where the heat flux is represented by the Fourier's law. The surface area dA sub y is perpendicular to the Qy, which is dx times dz. C. Replace Q sub y with 8.2. Since dx dz are fixed, both can be taken out from derivative partial y to form the differential control volume dV. In z direction, A, the conduction heat rate difference at the location z and location z plus dz is represented by its derivative using Taylor series expansion. B, the heat rate Q sub z is the product of heat flux and surface area, where the heat flux is represented by the Fourier's law. The surface area dA sub z is perpendicular to the dz, which is dx times dy. C. Replace d sub z with 8.3 d. Since dx dy are fixed, both can taken out from partial derivative z to form the differential control volume dV. 4. Plug in equation 7.1, 7.2, and 7.3 into equation 5 and back to equation 7. 5. Next, cancel out the differential control volume dV to get the general conduction differential equation, which is represented in equation 9. B. A summary of general conduction heat equation. First, in Cartesian coordinates, equation 9 represents the first law in differential form. It states that all the conduction heat into the system and out of the system in x direction, y direction, and z direction, plus the energy generated within the system is equal to the energy stored within the system. Equation 9 is second order in x, y, and z direction respectively, and first order in time. Therefore, it requires specifying 6 thermal boundary conditions and 1 initial condition. Second, in cylindrical coordinates, equation 10 represents the first law in differential form. It states that all conduction heat into the system and out of the system in r direction, phi direction, and z direction, plus the energy generated is equal to the energy stored. Third, in spherical coordinates, equation 11 represents the first law in differential form. It states that all conduction heat into the system and out of the system in r direction, phi direction, and theta direction, plus the energy generated is equal to the energy stored. Equation 10 and equation 11 is derivation leaves to student practice. C. A summary of heat rate equation for single walls. Our ultimate goal is to get heat rate and heat flux for the plain wall, heat rate and heat rate per unit length for the tube wall, heat rate and heat rate per unit volume for the spherical wall under the full assumptions 1, 2, 3, 4. In the following 3 slides, you will see the same pattern of steps to derive the heat rate equation. For plain walls, heat equation, thermal boundary conditions, temperature distribution, heat flux, heat rate. For tube walls, heat equation, boundary conditions, temperature distribution, heat flux, heat rate per unit length, heat rate. For spherical wall, heat equation, boundary conditions, temperature distribution, heat flux, heat rate. The detailed derivation of heat rate equation will be represented in Topic 2, Part 2. See you next time.